oxygen needs how many? Nicole in the front? 8. And again, watch my math here as I'm talking and writing and watching your faces. Then let's think available. Carbon comes with how many, Emily?
4.
4. Each oxygen comes with how many, Sarah?
7.
Look where it is. It's in the 6A family, so it must be... Did you say 6? Okay, I thought you said 7.
I did it first and I changed.
Oh, okay, okay. I thought you guys were just putting me on here because I heard 7. Did I ever tell you what, my sister, when she was in college, they had a teacher they really just could not stand, and he had a balance issue. And so, to get at him one day, somebody makes a signal, a cough or something, all the students in the class simultaneously lean to the side, and he fell over. So I'm like, we're pulling it fast without me here. Okay, so let's see, 12 plus 4 is 16. And, you know, I said I was the older, bigger, meaner sister, I believe, didn't I? What about the unequal sharing? I mean, she did some stuff too. I wasn't the only one. Okay, so we're going to share, Bruce, how many? 8. So, who's our central atom here, Nina?
Carbon.
Carbon. Now, we know to build around it, and, well, we're in chapter 7. I don't care where we stick those oxygens, top, bottom, to the side. I've said this before, but I'm going to keep repeating it. Lewis dot structures don't show you molecular shape. They lead us to it. It's a blueprint or bookkeeping. Now, I got to share 8. Can I have just single bonds? Is that going to work?
No.
No. Okay, what would be a solution, Marco?
Have 2 double bonds.
2 double bonds are going to cut it. Does anybody think, though, of another possibility to share 8?
Triple.
A triple and a single. Let's go ahead with that. I mean, it's not likely, but it's going to fulfill the letter of the law when we check it out. Okay, so let's go ahead and let's go back to this one. Each of these oxygens are in the same environment. So each of these oxygens need how many more pairs, Timothy?
2.
2 more pairs. Now, notice I mentioned last time, you got to be careful. Am I asking about pairs or am I asking about electrons? So you got to be up on which one you were just asked. So both of those need 2. Okay, this guy in the middle, Allison, how many more pairs? 0. Okay, now let's go down here and let's finish it off. Andrew, how many more pairs on this guy? 1. And this guy over here? 3. Let's see if they both fulfill the letter of the law. Okay, let's see. We have 8 to share. 2, 4, 6, 8. 2, 4, 6, 8. Either one works there. Okay, then available. We have 16. You always have to use everything in available. No more, no less. So 2, 4, 6, 8, 10, 12, 14, 16. Check. And 2, 4, 6, 8, 10, 12, 14, 16. Check either way. Okay, now, if you took these two, and let's say there are 2 different and okay structures, and you took it someplace to measure bond length and bond strength, what would you see different about the 2 structures? Yeah, you're going to have a really strong short bond and a longer, weaker bond. Remember the day I tried to save Meredith from jumping out of the hotel window? Points of contact. So if they both turn out to be identical in length and strength, this is a better structure. But Lewis dot could be either one. If you gave me this, I would say, yeah, you're right, because it fulfills everything. First?
Does that mean it's going to have 3 forms of resonance?
Okay. Yeah, and I'll talk about that when we get there. Okay, so now, on this chart, and again, it would be really great if you have your chart from your lab manual out, because just maybe we'll be doing some of the same that you can work out. Okay, if I want to know, and let's just think of this one right here. Let's just look at it. Pedro, how many atoms around the central atom? 2. That's a wonderful answer, because I don't care that this is a double or this is a triple bond. We're talking how many atoms directly bonded to the central atom? 2. Okay, how many lone pairs, Hina?
0.
0. So our number of things, Tran? 2. Anytime you have 2 things, remember the 2 cat story? What's our orientation? Right here. Kashan, do you remember? Linear, good. And if we do not have any lone pairs on that central atom, this answer will be the same. Okay, now, we're linear.
I'm sorry, can you say that exact sentence one more time? The molecular shape will be the same as what?
As long as you don't have any lone pairs on the central atom. And we haven't seen an example of that yet, but we will this morning.
Okay, so when there's a lone pair, then you go to what, like the names that you gave us, and you'll go
Yeah.
to one more. Okay.
And we'll see that. We'll see it numerous times this morning. Nina?
Your number of things is not including the bonds.
No, it's number of atoms. That's why I'm very careful. Look up there. I've spelled it out better. 3rd column. Number of atoms directly bonded to the central atom. It doesn't talk about doubles, triples, anything. Number of atoms. Because if it is a double bond, when it's the cat story, where the first bond goes, the second bond has to follow. So you got carbon here, oxygen, oxygen. Okay, so we say linear. Hold up your linear. Everybody got one? I want to see it. Linear's in the air. Why bother? It's just a representation. Well, she asked, why don't you put 2 thingies at the end? Hey, I don't care. If it's more beautiful, go ahead and do it. But it's not necessary. Okay, linear, linear. Everybody okay with linear? Russell, what's that mess back there? Playing. Where's your linear? And share with Pedro. Get some stuff. You know linear, obviously. Okay. He's got the molecular model dog set back there, I think. Okay, we got linear. Now, bond angle here is going to be what, Antonio? If it's linear?
180.
180. Okay, because when you talk a bond angle, remember way back in geometry or trig class or somewhere, to have an angle, you got to have 3 points, like angle ABC business. Okay, here we're talking nucleus to nucleus to nucleus. So that's 180 degrees. How do you know that? Because probably some middle school teacher pounded that into your head. Linear is 180. If you don't believe it, you get out one of those little things and you can measure. Is that a protractor, I think they're called? Okay. Get out a little protractor and you measure it if you don't believe it. But everybody seems to know that one. Now, we ended the hour last time. If I go ahead, this would be, see this back here, that was the valence, or the Lewis-Dot structure. This is really the Vesper sketch. Recall when we started this chapter, first a little preview, we have 2 major theories to help us understand molecular shape. One is the Vesper, valence shell electron pair repulsion theory, or the CAT repulsion theory. Years ago, back in the 90s, I went to a conference in New York, and I met the guy, Dr. Gillespie, that came up with this Vesper theory, and he gave a talk. He was from some Canadian university. I wanted so badly to go off at break time and say my CAT repulsion theory, but I thought he'd think I was too nuts, so I never shared my repulsion theory with him. And the other one, the other theory is VV, or valence bond. Your book, in every section, they do both. That is, in my opinion, a big mistake. We're going to go through the whole chapter using the Vesper, and then we're going to go back through it using valence bond. But it's going to be 90% of the time on this Vesper stuff, which is the CAT repulsion theory. Okay. Now, we talked polarity. And polarity is something that will haunt you in 1412 and organic or any chemistry class you take. And I think it's the most sophisticated idea I teach all semester, because you can talk about the polarity of a bond, but then you can also talk about the polarity of the whole molecule. and you can't talk about the polarity of the whole molecule, which is what this column is about, because I've worded it better over there. I've said polarity of molecule or ion, if it's a polyatomic ion. We're talking about the whole thing. But let's take it from the top. Carbon to oxygen. Who's more electronegative? Shout it out.
Oxygen.
Oxygen.
Where'd it go? Okay, oxygen is. So, is this a polar bond?
Yes.
Yes. And we can draw a force that direction. Okay, is this a polar bond? Yes, for the very same reason, because anytime you have two unlike things, their electronegativities are going to be different. So, we have a force this way, and we have a force that way. Yeah. Did I have enough time to talk about two of you pulling my arms off? Okay. So, here's carbon in the middle. Force this way, force that way. If you can visualize that this is symmetrical enough, the forces would cancel, then you got to tell me it's non-polar overall. And that's the important part. So, carbon dioxide, is it polar or non-polar overall? Non-polar. Good. Now, can you see what horrid true and false questions I can come up with? Carbon dioxide. It has two non-polar bonds and it's non-polar overall. And you are going to shout false.
Say it again.
I say it again. I can talk faster than your brain can go. Okay. We have two non-polar bonds and it's non-polar overall. False.
It's too cold.
Yeah, it's two polar bonds.
I'm confused though, because in the notes, you've got polar listed as all two different atoms and non-polar as the same atoms.
Okay, but those are the bonds. You're back in chapter 7. This is a polar bond because it's two unlike atoms. And see, that's exactly what I said the students get confused about. I can talk about the polarity of a bond. That's what's in chapter 7. But in chapter 8, we got to take it on. See, what I did to you, I saved the pain for one time. So I didn't talk about just bonds. I taught bonds, and we moved right on to the whole thing, where we were talking bondage in here. Okay? So, non-polar overall, because these forces cancel out. Force, force, cancel. Now, what if I screw up the symmetry? What if I put a sulfur in the place of the oxygen? Now, I have a wimpy little force this way. I have a good strong force this way. It's polar. We got polar bonds and it's polar overall because I fouled up the symmetry. But if I go back, if I have either two oxygens or two sulfurs, I don't care, the answer will be the same. Now here's something I want you to keep in mind as we go along this morning. If we do this, and if this is on your table, for instance, all we have done is we have kept the same central atom. I have changed a family member for a family member, or if they're in the 6A family, everything is going to be the same. If you know carbon dioxide is nonpolar, then you know carbon disulfide is nonpolar, and you do not have to reinvent the wheel. So on test day, let's say problem 13, I have something about this. And problem 17, I stupidly put this. Okay? Hey, you know all the answers already. All right, now, Bruce brought up a good point a bit ago about this resonance idea. Since this is the more logical of the two, and here's why. This and this are identical. Their needs are identical. The chances are it's going to be a double and a double. But if you're really slick and an attorney in training, you'll say, oh, but this works. Okay, I'll go with that. So over here, Bruce, this is what you were asking. If you tell me 0 resonance forms, because you're only thinking of the first one, there's nowhere else for that double to go, really. Remember, you have resonance, you gotta have multiple bonds. But if you're slick and you're an attorney in training and you think of this, okay, so now we got these two, but the question then would be, how many resonance structures total? What would you say?
3.
3. Exactly. So I would take here 0 or 3 in this particular case. Usually it's very clear what it's going to be. Yeah, Bruce?
And that's going to change your polarity as well, right?
Okay,
If
not
you have
really.
a triple bond is not going to pull more? Okay.
Okay, Bruce had a good point. Remember the rhinoceros story and the unicorn and the dragon business? This isn't real. This isn't real. You take those 3, you'd mix them all up, you'd end up with these 2 would be equal. Okay, so polarity will not change, but that's a fantastic thought.
How do we find the resonance again?
Okay, if you could move, like, if you could move a multiple bond around to another spot, now you're not moving atoms, you're just moving multiple bonds. This and this, these would be 2 resonance structures, because I moved one of these over to the other side, and then I could draw a third one by putting the triple on this side. When you think resonance, you gotta pretend your molecule is nailed down, is not rolling and tumbling. And you could distinguish between the 2 oxygens. And you can, if you used a different isotope of oxygen over here, then you could distinguish which was which.